Thank you very much. And my talk is very much in the direction of unsupervised methods, but very definitely I will be dealing with stochastic approximation in many ways. So I'd like to run through quite a number of different themes, but it will definitely include some application domains, and later I'll be just indicating to you where they have been published, and also I'll be making the data available and such like. So, in summary, therefore, it is using random projections for high-dimensional data. Now, I will be beginning, though, with a more simple application in astronomy, and just detailing the basic aspects of what the Bayer metric is. The Bayer metric, which is also an ultrametric. Now, I also want to point out how this differs from some other mainstream work in random projection, which is quite widely used nowadays for basically facilitating the construction of a reduced dimensionality mapping of the data. And this work is somewhat different, and therefore I think there's innovation and novelty in it, which is important to stress. Right. Fine, just for what is at issue here, and I'll just be pointing out a number of aspects. Just by the way, in terms of PCA, principal components analysis, CA stands for correspondence analysis in this context. And as we'll see, it is largely the objective is constructing a hierarchical classification, and this is done through scaling the data, and I'll talk a little bit more about the fact that if we have the data properly scaled, we can induce a hierarchy in essentially linear time, linear computational time. As we know, just by way of background, typical agglomerative hierarchical clustering is a quadratic term requirement in terms of computational effort. Overall, of course, hierarchical clustering, or clustering in general, is with the objective of search and discovery. And as you, I'm sure, know, a hierarchy is associated with an ultrametric topology. What is that? Well, just simply is in the case of the triangular inequality, which is one of the important properties of a metric. In the case of ultrametric data, we have the so-called strong triangular inequality, and that gives rise, therefore, to the distance on a tree, which is the ultrametric topology. Okay, I'm going to start now then with the looking at the Sloan Digital Sky Survey data, and then look at chemical data in this context. Just by way, though, okay, to begin with, the Bayer ultrametric, and very, very simply described here, we have an indication as to how you define the Bayer metric, which is simultaneously an ultrametric. And these are just two scalar values, x and y here, and we find that by convention we can have these bounded by 0 and 1, so consequently we're looking at significant digits and finding that we have 4 being shared by the two numbers, 2 being shared by the two numbers. They differ with this third digit of precision, and therefore the overall digits of precision here, by the way, just happen to be 3 just by this little trivial example, and we find therefore that we have this as being the case, and therefore define the Bayer distance to some base, and this base may well be a p-adic number, but an m-adic number, as it is generally as is generally expressed, is quite adequate, and for the decimal base 10 numbers, which we'll be dealing with in all of the examples, this will be quite appropriate. And then the exponent is minus to the number of digits which are shared, 2 in this case. And this then it is a distance which is furthermore an ultrametric distance. In other words, represented directly as a hierarchy or tree. Therefore, it also defines an ultrametric topology. So find, therefore, it is a matter ultimately, and this is just in summary of what is being done here, is to read off a hierarchy from the data in a very direct fashion. And in this case, therefore, it's the longest common prefix distance. Okay? And just indicating too that de facto, like in practice, it is really a type of hashing scheme where we are essentially reading off from the actual values of the data the cluster membership through the set of digits which are in the value that we're dealing with. And this is the astronomy data used. And astronomy data has, in terms of the essential coordinates, right ascension and declination, which are the latitude and longitude of astronomy, and then the z direction, coordinate, third dimension, which is redshift, which is distance. It is also quite possibly speed of movement, and it is the third dimension, simply. And in practice, spectrometric redshift is more difficult to obtain in terms of the requirements. Photometric is collecting light, and it is a much easier method to obtain this third dimension. And consequently, the problem essentially here is to regress the spectrometric and therefore more sophisticated, more accurate definition of that third dimension from the more easily calculated other photometric measures. And a certain number of this is the okay, this is still the astronomy one here. And then looking at the use of the air distance, this is just the part of the sky which was covered in terms of this data, which is represented by the black area here, and this was just looking at this data. This is just a typical sample of right ascension values, declination values, and then the two sets of values which we want to do basically nearest neighbour regression, so that one would be predictable from another. And I'm just going to quickly just show the outcomes which are obtained from using the Bayer distance to find the associations between the, as I said, relatively easily determined photometric redshifts and the spectrometric redshifts, which are the more better precision ones. So it's cluster-wise nearest neighbour regression, but here, unlike sometimes in terms of cluster-wise, let's say regression, let's say where it is a matter of geospatial data or otherwise, where the cluster would perhaps be regional or otherwise. Here, the clusters are related to the precisions of measurement, and this therefore leads to a very appropriate way for mapping the data into cluster bins which are related to their digits of precision, and thereby picking up the values which we want to associate with each other. So the data are binned or clustered in a very fast way. So, so therefore, again, just stressing that cluster-wise here is not in terms of spatial coordinates, right ascension and declination, but rather within the data itself in terms of precision. Now, unfortunately, these are little videos, but they won't show on the PC, which they're on because they were done on my Mac. Basically, we have here precision and digit. This is the set of digits, the precision of measurement and what digit is at issue. And while there is a lot of commonality in the two data sets, one is spectrometric, one is photometric here. While there's a lot of precision, there are also areas where there's quite clear distinction. And consequently, being able to pick up, to basically focus on those differentiation aspects of the data leads to the possibility to find patterns in the data related to their precision of measurement, and consequently the data are clustered effectively through simply reading off the bare distance, the longest common prefix distance in the data. And the type of outcome then which is obtained, and that's all I'm dealing with right now today, just is that with so many digits of precision that we will have such and such a level of accuracy of the matching of the data, and therefore the effectiveness of this is very much related to the linear time computational requirements, namely through direct reading of the data and simply binning of the data in terms of their cluster properties at the different levels, right, because of the longest common prefix distance. So, in other words, this is something which caused a little bit of trouble, in terms, I remember, of a discussion at one point in the past. While I am talking about determining a distance, I'm simultaneously talking about finding the cluster membership of what we're dealing with. And in a sense, therefore, it is directly finding the cluster membership without needing to actually specifically address the definition of distance. If you see what I mean, we're doing these activities effectively simultaneously from an algorithmic point of view. Okay, and then looking just at the chemoinformatics now, because now I'm coming to high-dimensional data. The data there was nicely just univariate, essentially, so fine, but the principle was established. So what do we do then when we have a chemical compound represented by a large Boolean or binary string? And this type of string is very much relevant. It's one approach towards the specifying of the properties of chemical data. And of course, very, very, very important in so many areas in this context, as just sketched out by some of the points made there. So we have various systems in use, and the one which happens to be in use is this one here. It's an indexing system. And this data was provided by a co-author of the paper, which was written quite a while back, who works for a chemical company and who provided this data. So I'm not really interested myself, quite frankly, too much in the chemistry, but I am interested just in clustering and the ability to form clusters very, very, very effectively. So the question therefore becomes immediately, for very high dimensional data, how are we going to handle such issues? And then the aspect which is used is to use random projection. And in the just over 1,000 dimensional space, and then on the basis of the projected values, and actually on the basis of consensus, or at least mean projected values, I'm going to be looking at that in terms of the outcome, and just mentioning some of the quite extensive experiments which were carried out to verify that the outcome was of very high quality. But also I will be pointing out the fact that this is actually differing from a mainstream use of random projection, and I'll be coming to that just in a few moments' time. So we have this data, and this again, unfortunately, is a slide which has a bit of an animation in it, but because I'm showing you a PDF version of it, you're not seeing the animation here. But anyway, what I want anyway just to mention here is that while there is a large self-evident and intuitive aspect of random projection, there are also aspects whereby, let's say for instance, we have these three little green dots depicted for illustrative reasons just here. We have them very much associated in terms of their projection on the random vector, but we also have, of course, a red dot over here which is some distance away. So we basically want to have an approach which will perform quite well. Here we have another version of problems that can arise, but in practice, number one, in very high dimensions, there is a very effective ability to do random projections in this way. Secondly, there is the aspect which I will be dealing with of having a consensus random projection through taking a mean set of random projected values. And that can be found to work also very effectively, especially too in high dimensions and when there are a sufficient number of random projections used in order to have the consensus of them. So in the case of the chemistry data, they are normalized, well, in a way which is analogous to both the use of the row and column marginals as masses to be used in a weighting of profiles, as the term is in correspondence analysis, and that in turn is quite close, it's analogous, I should say, to the TD-IDF approach, which is widely used in information retrieval. The inverse document frequency type, term frequency, inverse document frequency type normalization, which is typically used. So this was used, therefore, to normalize values in the initially Boolean or binary matrix, if one wishes to view it in matrix terms. And then that at least had the aspect of ensuring that the values were between 0 and 1, and that was of benefit. And I'm going to be using, in this work, what we've used is uniformly distributed random axes. Again, that differs from a mainstream approach which uses Gaussian values for the random axes. And there are two approaches which were used here. One was to look at different values of precision quite directly in the data and essentially read off connected components in that data on the basis of their projected values. And another approach was to more explicitly use the Bayer distance in terms of looking at the commonality relative to first digit precision, second, and so on. And just in terms of this, I think I just want to see if I've got one other slide on this. No, I want to just actually look at some other, just another example right now, but it really does allow an inducing of the hierarchy on the data. And I'd like just to point out that in the case of the chemistry data, quite extensive tests were carried out relative to k-means clustering, and with very large commonality of results. So, in other words, the results were assessed relative to that, relative to the, let's say, connected components in one case, which were found by lowering the precision of the data values, and closely allied with that, the use of the Bayer hierarchy, namely looking for the cluster affiliations or memberships at different levels of data precision. And de facto, again, I would say that we have a hashing approach in the sense that we're basically just reading off from the particular values the actual, well, it's a particular numerical representation of the data, the longest common prefix, let's say. You know, that's what I mean by indicating that. And because the data is inherently structured as a hierarchy in all that I'm dealing with, so we are really dealing with data which is directly read off into a hierarchy, and definitely faster therefore than traditional agglomerative or potentially also divisive, of course, hierarchical clustering approaches. And a very basic motivation for all such work is the embedding of data into an ontometric topology. In other words, the inducing of a hierarchy on data. Why? Because of effectiveness and use and benefit in search and discovery, and also in other ways as well. There are areas which are of interest from my point of view at the moment in terms of even psychoanalysis and so on, because there are psychoanalysts who have argued that unconscious and subconscious reasoning is very closely allied to hierarchical viewpoints, and consequently one can argue that that really does relate strongly to an ultrametric context and representation for such reasoning processes. Anyway, just going to look at another example now, and also I'll have some just a nice example of a display potentially coming out of this. And this was used actually. This was started by using Apache Lucene and Solar for indexing, and in particular there is a similarity coefficient which is used in Apache Solar, which is has the term more like this, MLT, more like this, and it's a field-based approach where the fields are predefined, maybe in a document, for instance, one might have different fields, and furthermore it uses actually a TD-IDF normalization, as is usually widely used in information retrieval. Like I say, that therefore is used. So therefore this is just an example of a graphical user interface where a large number of chemical recipes were indexed and made available for search, and based on that there was some work just carried out on correspondence analysis and just representing the most important, some of the most important terms in the principal plane as purely as an indicative and helpful approach here. One thing also which was done actually was to look at the coordinates in the principal factor plane and set those up also to allow therefore proximity to be availed of in a solar search. So implemented in solar using principal factor plane coordinates, so that you could find something, let's say, which was in terms of recipes close to Italian in terms of Italian cuisine. Right, okay, that's another matter. What I'm mainly interested in here is the more like this term, which should be visible just here. In the case of Apache Solar, you have this entity here which is clickable, and that will give you a number of other recipes which are considered to be more like this. It's just the similarity measure. So therefore, using those similarity measures, they were used to carry out a bare clustering of the data. This was this is the going now to a different data set. Funding proposals coming from the National Science Foundation in the US, and this was a matter of a sparse similarity matrix, similarities defined from more like this in Apache Solar of 10,000 of these documents by potentially 30,000, including the 10,000, but other ones as well. And therefore, to look at the possibility to process that data very effectively. And I'm just really dealing right now with just the way that was done. And there are random projections using, as I'll express in just a moment or two, uniformly distributed random projection coordinates, and using a sufficient number to have convergence in terms of the mean. This has been looked at very, very much in terms of the fact that having a sufficient number of random projections, that the mean random projection will converge. And have a few other things to say about that by way of explanation in a few moments' time. And looking at this, therefore, looking at the layer 1 clusters, okay, using the same digit, this is the bare metric, but representing it in a particular way here, and then the layer 2 clusters, given the same first digit, having the same second digit, etc. And then this is, of course, then the longest common prefix distance, which is the bare metric or ultrametric. And then this can be nicely represented, but this is purely a depiction of the data in terms of what is shown here. It is in just over 10,000 documents, which are the entities we're dealing with. And this bottom layer is the first digit of precision, so that we have the documents in sequence here relative to the mean random projection and with the first digit precision shown in the bottom layer, the second digit precision in the next layer, in the next layer again the third digit precision, and so on, and using false colour coding just as a depiction of the data. So it's a depiction of a hierarchy or of a tree, just done in this way purely to just illustrate the overall the overall data. And fine, so it's only just a visualization of the data, and a bit unusually maybe visualization of a tree or hierarchy done in this way, and all based on the random projections then, and on the Bayer metric. So I'm going to look a little at is this relative to more conventional use of random projection, where the aim is much more to project the data into a lower dimensional subspace, and then to have accuracy of interrelationships in the data when the data is in that low dimension. Whereas here the aim is different. It is to have a consensus, one-dimensional or scaling of the data that represents relative proximity. And therefore I'm going to just explain why, or to begin really, how these are just different, and therefore to justify basically the approach which has been used by us in regard to this. So 2 following slides. One aim is the relative clustering properties in the data. What exactly does that mean? And then the second thing is the Johnson-Lindenstrauss lemma, which is a basis for random projection when the low-dimensional mapping is the main aim. So I want to just look at that. And to begin with, I'm taking a figure from this paper published quite a while back. Hierarchical trees can be perfectly scaled in one dimension, and this is both motivation and justification for the approach used. Why? Because we have a hierarchy here. If you consider a one-dimensional mapping which could allow the relative proximities between the entities that we're clustering here to be represented adequately in one dimension, one can have that as a fairly intuitively self-evident aspect of this data, whereas, of course, in terms of a fairly usual agglomerative hierarchical clustering, these entities that we're clustering are, of course, from some given dimensionality. So, in other words, we have another representation of our entities which is in one dimension. It's in a so-called seriation. The word seriation is quite often used for certain areas of data analytics going back a very long time. But the fact is that this therefore is a scaling of the data in one dimension. And that's a nice viewpoint which was explored somewhat in that article. So I want to just therefore use that as a fundamental basis for the work which is being carried out. It is a matter of having the data scaled in one dimension in such a way that a hierarchy can be read off the data. And that's important in its own way. And now we're looking at the traditional mainstream approach, which is not the case here. And again, I'll just have a few further words as to why I am very happy with the approach which has been adopted, which does not use this approach. But just to mention that we have our, let's say we have UNV in the original space, and we map that then, UNV and all other points, of course, into a space of lower dimensionality, and this is therefore just, let's say, an L2 metric, Euclidean distance squared between them, and bounded. And furthermore, there is the the aspect of bounding in terms of this epsilon term, and furthermore the fact of the computational aspects of this, which is a separate matter relative to the point I'm making here. Just want to make this just clear as an aspect which characterises the mainstream approach to finding a low dimensionality embedding of the data. So just in 2 or 3 slides, I'm just going to talk a little bit about the fact that from basically using this article by Kasky, going back a while also, in the area of the traditional mainstream approach, it is the random projections are Gaussian, and while the reduced dimensionality space through use of a range, a number, potentially a large number, but that really is to be assessed in practice. But the orthonormality of that is not guaranteed. But there's a nice quotation from Heck-Nielsen that the number of almost orthogonal directions in a coordinate system that is determined at random in a high-dimensional space is very much greater than the number of orthogonal directions, which is therefore means therefore, of course, that the approximation is quite appropriate and may well be in practice. And let me just see here. This is just again summarising the mainstream approach here, with the possibility that some other variants are possible relative to the random projection axes. And therefore, in this article, it's interesting that it notes that the uniform distribution is easier to generate than normals, but the analysis is more difficult. So the analysis has gone some way, really, in the work which we've been carrying out in terms of the use of uniform axes, uniformly distributed values in their coordinates, and taking the mean then and so on. Now, I would very much associate this work though with data concentration or data piling, which is well known that as the dimensionality increases greatly, that there are particular properties. I've referred to it in a paper as the remarkable simplicity of very high dimensional spaces, where for instance, for a start, pairwise distances become equidistant and so on. Hall, Marin, and who else published on that in Journal of the Royal Statistical Society going back quite a long time. David Donahoe has also published in this area, of course, and so on, just in terms of the particular remarkable effects in very high dimensions. So fine, we also find, okay, that this is in regard then, in particular, to the uniform axes, random axes, uniformly distributed, and some just properties which follow from that. So, in other words, the effectiveness of this is, number one, empirically demonstrated, and number two, is related to both central limit theorem and the data piling in very high dimensional spaces. Here there is just a mention of the empirical evidence from the contexts which have been at issue. And as indicated, that the objective is to not to look at accuracy of low-dimensional representation, but rather to rescale the data such that fundamental properties of the data are available for directly reading in terms of hierarchical properties. Summary remarks, therefore, just okay, this is something which is essentially, which is looked at a short time ago, and then the visualization, then just to repeat really, is just as shown here in terms of this work. And one of the aspects which I'm interested in currently in terms of such work is to look at further linear time, if this is certainly the objective, linear time simplification of this through actually looking at other digital digit basis for the work. And so far, some experimental evidence has shown that p-adic representation is very useful. In other words, a base which is unlike the base 10 which is used here for the different digits, rather to use a base which is a p-adic number, 3, 5, 7, etc. So an aspect then here which is interesting enough really in terms of traditional clustering is to look at distances, determine clustering structure, and then perhaps in many cases to determine a partition depending on, of course, on what one is doing, the hierarchy itself can be maintained. Here we are actually building a series of partitions through the binning of the data into clusters at different levels of precision, and thereby then the hierarchy is read off from them. Now, overall in this work, I've just basically sketched out things for you in the time available and mentioned, of course, referred to the different application domains and so on. So what I'd like to do now is point to where you can find out further aspects of any of the aspects that I've spoken about. And I've set it up on a website of mine, and I'm making it available to you, and it includes quite a lot of the software, quite a good deal anyway, maybe not everything, but a lot of the software which has been at issue here, and so on. So that's the website of mine here, right? And I've set this up here and with these things available. And because some of the papers which I also put there are the publication versions and so on, I thought it's better not to put this totally into the public domain. So I've set it up with a username, courses, and a password which is uppercase W-E-L, figure 1, uppercase C-O-M-E, just to mention that is a figure 1 in the middle, just in terms of the password. So if there's any difficulty in accessing that, just let me know, but that should be absolutely fine. And just 2 slides, this first and the second one just now, just to show you what's there. So first of all, I've put this talk there in terms of what I've just been dealing with right now. Secondly, quite a lot of the OR code used in various contexts has been put there. And then the data sets used, I've also just made them available if of interest. The chemical data set it's in a zip file. It's actually in a particular encoded form, and consequently I've got, I've got a program there we can see which will allow the data to be extracted from that particular encoded form which is there. And that's another, by the way, text version of 1,000 of those chemicals. There's another version, again in text, just as zip files of 7,000 of them. And then let me see, where is the interesting that this slide's just been cut here. Actually, just here I've got the astronomy data and those document similarities that were produced originally in Apache Solar. I've just got the data set. The output, of course, just those similarity measures of a very sparse matrix, and they're available on this page. And then the very final slide just is also accompanying that is how did this happen? Relative to what I prepared. Yeah, sorry, that's no one. Yeah, step back just. Yeah, that's what I was showing. I'm trying to. No. Those have been cut for some reason. Funny. Anyway, this is the last slide here. Just that, also on that page, there are various papers which have been published in this area. One which is related to the astronomy data was published just there, and the one in chemistry is this called Science Journal of Scientific Computing. And then there are a few others which summarise all of the different properties and even drawing. Well, there's an indirect, though it's an indirect link, quite frankly, to formal concept analysis and such like. And then there's these some more recent papers then are related to the to further investigation of this. Just mention, by the way, that the areas of particular interest right now, from my point of view in this work, are number one, implementation as key value pairs for distributed computation. It would lend itself very, very well to that type of approach. Secondly, an area certainly is stochastic and iterative convergence properties of finding eigenvalues and eigenvectors. And this is related very strongly to that approach to stochastic approximation and so-called direct reading algorithms for eigendecomposition. So that in turn is an aspect which has been written up in some very recent work, and this is continuing. And if, by the way, this is of interest from the point of view of your work, I would quite like to number one, to know about that, but number one, perhaps to know about the work that you're doing, and in order to take such work further. I find that efficiency and effectiveness are both very well addressed in this domain, and just as mentioned, the way is open, as I see it, for large-scale distributed use in very big data contexts of such work, and that I really view as a very, very strong point for this approach to analytics, which follow from all aspects of what has been dealt with here. And there I will leave it. Thank you very much.
Thank you very much. Perfect schedule so far. Maybe we have time for one question before the coffee break. If there is one. Yeah.
I'm not sure to have well understood your bare distance. You look at, for example, your example 0.425 and 0.427. If you have 0.421, you have the same distance, same bare distance between 0.421 and 0.427.
Yes, insofar.
So you have a topological space which is not zero. You have a problem of separation of the points.
Sorry, I didn't quite understand that. But look, it's the longest common prefix distance, right? So, so yes, you have a distance which would be shared in a case just as you mentioned, but don't forget that the distance would be somewhat large. Whereas if it's to be a distance which is much more smaller, you will have a lot more digits shared. The longest common prefix will be larger. Consequently, the distance will be smaller. Right? Is that okay? So, in other words, that was just a small toy illustrative example, of course. But the principle, I hope, is very clear from it. And it is, like I say, just describe or characterising it or speaking about it in terms of longest common prefix metric is quite adequate, really. Essentially, it's what's used in network addressing and how IP addresses and so on are processed and the like, and that's something I would like to just pursue a little bit further, because really that effectively is what is being done in a context where you want the initial values of what is being of the entities and the numbers, which if they're in numeric form, you want the initial values to be shared. The greater the number which are shared, that indicates the greater the proximity is between what we're dealing with. So very, very simple. Very, very simple in many ways, but fascinating in the sense that it's not just metric, but it's ultrametric at the same time. You know? So in other words, representable as a tree, as well as representable, of course, in a Euclidean space.